share our latest work, the conceptual design of a robotic building envelope assessment system for the energy efficiency. Before I share our work, we know the energy efficiency of a building is greatly affected by its envelope, the windows, walls, and other components that enclose the building's indoors environment. Defects in the building's envelope constructions can lead to the heat loss, water leakage, and moisture damage. All of these defects will cause the lack of the isolation or the thermal bridging. The energy will be lost from the inside of the building to outdoor environment. Here, I would like to share two numbers to show why we urgently need the energy efficient building envelope. The net effect is that the building envelope counts 25% of primary energy use by the buildings in the U.S. and the average of the buildings the average of the U.S. buildings approached 20 years old by the end of the 2015. These issues will continue to affect a growing numbers of buildings' envelope durabilities as their components age. To address these problems, currently U.S. energy policies require the buildings to be inspected regularly. However, the building inspectors facing a number of the challenges. First, the inspectors can be labor-intensive and hazardous. Inspections for the large buildings are usually limited in scope to conserve the inspectors' time and energy. Accessing the envelope area, such as the roof and the attic, can be dangerous for the inspectors. Additionally, some inspections tours are invasive, like the blow doors test and the wall scope can be identified the envelope defects, but require the occupants to leave the buildings and damage the components. Also, the infrared thermography is used to survey the issues non-invasively, but the infrared imaging has its own limitations, which respect to the sunlight, materials reflectance, and the detecting the moisture issues. All of these challenges points a need for a variety of the inspection tools and capabilities that are non-invasive yet accuracy in the detection envelope issues and ultimately make it safer and more efficient for the building's inspector to work. By review's previous work in the building inspection area, we found that our pioneer used the drone as a mapping tool to rebuild the 3D environment based on matching image and the beam model. Also, there is a team come from British which used the infrared drone to detect the thermal bridge and the air leakage. Recently, the ground pattern radars or the GPR was extended to inspect the invisible moisture damage which behind the wall. Although first two methods are greatly start to reduce the hazard for those hard to access area, none of these methods provide the real-time feedbacks, and it still rely on the experience of the technicians to analyze the data and find out the defect points. Usually, their technician will use these tools to record the data. If we can combine these tools and applied with the latest AI algorithm on the inspection data, we will greatly reduce the experience requirements for these devices users. Therefore, here is our solutions to solve these challenges. A multifunction smart drone system called the EasyBot. The advantage of our solution is non-invasive, fast and efficient, and smart with the accessible cost. Our EasyBot could work in two inspection modes. When it operates as the flight mode, we can use it fast and comprehensive to scan the building envelope, or it can fly into attic to provide the 3D and the thermal information for those inaccessible area. EasyBot can also transform to the wall climbing mode. In this model, the GPR is attached at the bottom of the drone and scan the envelope moisture in the depth directions. To find out those defect points, we are mainly relying on these type of the data, such as the 3D point clouds, thermal image, and the radar heat maps. To better understand our solution, I will present whole system workflow here. When we inspect one new building, we were using the thermal camera and the 3D module, 3D sensor module to rapidly collect the data. Before it fly, we will do simple calibrations between two cameras to align the thermal image and the 3D point clouds. We will record all the thermal bridge and the potential leakage positions and displayed on our control tablets. Then we switch to the climbing model. We change to use the GPR sensor module to detail scan the building envelope. By aligning the thermal image and the 3D point cloud, we will apply the 3D registration algorithm with the thermal data. After this step, we create a 3D thermal map for whole building envelope. By adding the GPR results, we finally get the problem labeled 3D thermal map. For the detailed hardware design, our EasyBot have the 4 brushless motor and propellers with the rotation shaft, which can switch mode by changing the degrees between the shaft and the drones. We placed the battery and the control unit at the center of the EasyBot. In the flight mode, we set the thermal camera at the bottom and the 3D sensors at the front of the drone. Both sensors are placed on a 3-axis gimbal to extend the field of the view. When the EasyBot operates in the climbing mode, we removed the front sensors and the gimbals to connect it with a high voltage tethered cord for continuous power and the safety purpose. The portable GPR sensors are replaced the thermal camera to scan the details of the envelope. Our EasyBot never work alone. It's supported by our multifunction toolbox. The toolbox is designed durable and safety for the transportation. We can place the control tablets and the documents on the lid of the toolbox. For the left side, our toolbox has 2 levels. We use the top space to secure the drone during the transportation. At the bottom of the left side, we have plenty of the space to place the gimbals and the sensor modules. At the right side, we design it as the power zone. We can use the power supply when it's connected to the wall plug, or we can use that as the built-in batteries when we work in the outdoor environment. Here we use the Microsoft AirSim for the flight simulations in the 3 different types of the environment: the residential building, commercial building, and the attic environment. For our current progress, we are focusing on developing our prototype, which include modified the drone system, test the deep learning algorithm, and build the mock-up model, and test our systems in those models and in the real environment. Also, we attended the eRobot Prize, which organized and sponsored by the U.S. Department of the Energy. After the professional judges' review, our conceptual design was selected as the Phase 1 winner team out of the over 70 teams. Currently, we are building our prototypes and are ready to present for the on-site demos in the April 2022. That's all of my today's presentation. Thanks a lot, everyone.